Hello, welcome to another practice problem. We're going to do 9.3 out of the textbook. It says here for the following problems, the beam segment subjected to the internal bending moments at sections A and B. And for this problem, we want to sketch a side view of the beam and plot the distribution of the bending stresses acting at the section A and B. Indicate the magnitude of the key bending stresses on the sketch. Determine the resultant forces acting in the x direction on the specified area at sections A and B, and show these resultant forces on the sketch. Part C is the specified area in equilibrium with respect to the forces acting in the x direction. If not, determine the horizontal force required to satisfy the equilibrium for the specified area. So there's a lot going on. So let's just start with what we know. The first things that we do, looking at our diagrams here. The one on the right, we can take this cross-sectional view and we can find our neutral axis. We need to find where this is located, our y-bar, if you will. And then we also need to find the moment of inertia. Okay, and that will be the first thing that we need to do. So I've already done this because you should be very familiar in doing this. You can verify my answers if you need to, but the process, we just find for each shape, we find our y, and this is all in millimeters, and then our area, and then the moment of inertia for each shape, and then the difference between y bar and the y sub I, and then we find our parallel axis theorem, and we sum all these values together to get our moment of inertia, and this is our y bar. Okay, so you can verify my answers later, but with these answers, now we can move on to part A, step A, I guess. So I drew a little picture down here, which is going to, which is our side view of this this member, right? So if this is our side view, then this is A, and this is B. Okay. And so these little triangles that are the blue triangles that I drew on the outside of this is where our stresses will be drawn. Okay, so the black rectangle in the center is going to be, that's our member, and then we're going to indicate our stresses in these triangles. And notice the magnitude, the further away it is, right? So if we're from here to here, this is our magnitude, okay? And notice it goes to 0 when we hit our neutral axis, okay? So based on observation, we can look at our internal moments, the purple half circles up here on this other diagram. We have 5.8 kilonewtons per meter, or kilonewton meters, and 3.2 kilonewton meters. And both of this, by our sign convention, both of these are negative moments, okay? So we're going to find our moments, right? We're going to find the maximum moment, and you can do this by drawing your moment diagram if you want, but I'll just jump to what we know, and we can find our bending stress is going to be multiplied to the moment, multiplied to y, divided by I sub z. So we need to calculate the bending stress for each one of these points. So for here and here. Okay, so we know it's 0 at the neutral axis, but what's the bending stress on each one of these points? And so you have to calculate this 4 times, but I'm only going to show once. You should be able to solve for it on your own. But the bending stress, okay, for say the bottom part, the bending stress at B, right, is going to equal to our moment, which will be our negative 3.2 kilonewton meters. We'll multiply that to 1,000 millimeters per 1 meter for our units. Multiply to our distance from the neutral axis to this outermost edge, which happens to be our y bar, which I calculated before. It's over here, 181.154 millimeters. and then divide that by, actually we'll multiply this to 1,000 again. So 1,000 newtons per 1 kilonewton. And then divide this by our moment of inertia for the entire member, which is going to be 140739231 millimeters to the fourth. You calculate all this out, and you should get a stress at B be a negative 4.11891 Newton per millimeters squared, which we can then say our stress at B is going to equal 4.119 megapascals, and that is because we had a negative, that will be in compression. Okay, so do this again 3 more times to get the values at each end. And I'll just give you the values now. So this was this is all in megapascals, and so this is 4.119. Up here is 2.702. Here is 4.898, and here is 7.466. Now to calculate these values over here for A, you're going to use, because as you see I used negative 3.2 for B, and that was because that's the moment acting at this end. So if you just use 5.8 for the moment acting at point A, and you'll get those values. Now another thing I want to mention is where this is right here, we want to calculate these values too, right? Because this is where the top of the beam is, right? So what are these values here? And I'll give you those as well. 2.020. And the only difference between calculating these on the ends and this here is your y value changes. So you're only going to calculate the distance from the neutral axis to this point. And here is 3.661 megapascals. Okay, and since we determined that the bottom here, remember when I calculated this, the bottom B value is in compression, and we can just look at our diagram with these purple arrows up here, and we can make the determination, yeah, these negative moments are going to create a compressive force on this bottom end of the member and tension up here at the top. So what we can do for our tension, we'll draw arrows going out, okay, on both sides. That's not quite even, but you get the idea. And then for the compression, we'll draw arrows going in, okay? Okay. So that's our diagram. It's kind of sloppy, I'm sorry, but that's the general answer, I guess, for part A. It says here, part A, sketch the side view of the beam segment and plot the distribution of bending stresses. So the key bending stresses on this sketch. So that's the answer for part A. Okay. So for part B, right? Part B, it says determine the resultant forces acting in the x direction on the specified areas at sections A and B, and show these resultant forces on the sketch. Okay? So the resultant forces, right, to be able to calculate that, we're going to look at on section A for the resultant force on area 1, right? We can say our force A is going to equal this. If this was a distributive load, right? Think of a distributive load right here. We have a triangle, right? So this resultant force acting up here is going to be 1/2 multiplied to the height, so 4.898 plus this height, or I'm sorry, it's a trapezoid, sorry, 3.661, then multiplied to the area, right? So it would be 160 millimeters multiplied to 30 millimeters. 160 millimeters being the area of this top section, right? So when I said section 1, that's this section here, okay? That's the area of that. So calculating this out, so the resultant force acting on section 1 to 20,542 newtons, which just equals 20.5 kilonewtons, and we determined that was in tension already. And so the force acting on B, same process, 1/2 2.702 plus 2.020 multiplied to 160 millimeters multiplied to 30 millimeters. And then this will equal 11,334 newtons, which is 11.33 kilonewtons, and that's also in tension. Okay, so for our resultant forces, we'll add these to our diagram, and our resultant forces here are going to be going this direction and this direction, and this one was 20.5 kilonewtons, and here was 11.33 kilonewtons. Okay. So for part C reads, is the specified area in equilibrium with respect to the forces acting in the x direction? If not, determine the horizontal force required to satisfy the equilibrium. Okay. So what we can do here is sum our forces, basic statics, sum our forces in the x direction equals 0, indicate our positive. And we have our negative 20.5 kilonewtons plus our 11.33 kilonewtons, which equals a negative 9.209, right? So this obviously is not in equilibrium, so this is the horizontal force that we need to apply. So we need to apply a force acting on the horizontal direction equals 9.21 kilonewtons acting to the left. Okay, so and this will be the answer for part C.